In this video on subspaces, we have two objectives. First, we're going to define what a subspace is, and then secondly, we're going to do some examples where we decide if a given subset is in fact a subspace. We start with some preliminary definitions. First, we'll define what a subset is. If A and B are sets, we say A is a subset of B, written with this symbol that looks like a sideways capital U, if every element of A is in B. So it's very straightforward. If every element in one set A is also in another set B, then we say A is a subset of B. We can diagram that down here. If I draw two sets, here's the set A, it's inside the set B. Every element inside A is also in B, so we could say A is a subset of B. It's also true that since every element of A is inside A itself, we can say that A is a subset of A, and that's true of every set. Every set is a subset of itself. Okay, the book has a different definition. Some books use a different definition, so it's worth pointing out the alternate definitions here. An alternate definition of a subset is to use this symbol, and it means the same thing as this definition up here. So this reads A is a subset of B, and it means exactly this up here. Every element of A is in B. This notation, which is the same one that I use for a subset, this is actually a proper subset. So we say A is a proper subset of B, and what it means is A is a subset of B, and A is not equal to B. So if we come back down here to our example, A is a proper subset of B, but it would not be true that A is a proper subset of A. So if we wanted to write using the alternate notation, we could say A is a proper subset of B, and then we could say A is a subset of A. So A is a subset of A, it's a proper subset of B, but it's not a proper subset of itself. For various reasons, I've chosen to use this notation, mostly because this is the most commonly used notation for subsets. So if I want to write something like a proper subset where I want to exclude the possibility that A is equal to B, I'll just write this. A is a subset of B, and A is not equal to B. So this is equivalent to the definition of a proper subset, but we don't need these two different notations for subsets and proper subsets. We just have one notation. This symbol that looks like a sideways U means A is a subset of B. And if I want to exclude the possibility that A equals B, I just say A is not equal to B. Now we come to the main definition. In this section, we define a subspace. So first off, notice the difference in these words, subspace and subset. We just defined a subset. Now we're defining a subspace. They are very similar looking and sounding, subset, subspace. So just be careful not to confuse them. We say let H be a non-empty subset of a vector space V, then H is a subspace of V if H is closed under vector addition and scalar multiplication. An alternate definition for a subspace that is logically equivalent, in other words, given this definition, we could prove that this one is true. Likewise, given this definition, if we started with this definition, we could prove that this one is true. So the alternate definition says let H be a subset of a vector space V over a field F, then H is a subspace of V if H is a vector space over V. This one is a little less obvious what that means or how do you check that. We would have to check all 10 vector space axioms to decide if H is a vector space, at least based on what we know already. But it turns out that sometimes this is an easier definition to use. Most of the time we will use this definition, however, and we will focus on closure. So if H is a subset that is closed under addition and multiplication, then it is also a subspace. So we can think of a subspace as a closed subset. And I'll put that in quotations because that's not a formal definition. That's just a way to think of it. It's a shorthand way to think of it. The word closed means closed under vector addition and scalar multiplication. So as we do examples, and as we're trying to decide if a given subset is a subspace, we basically just want to see, is it closed? Something that's really useful when we are trying to do that, when we're given a subset and we're trying to decide if it's a subspace, is to focus on the zero vector. Since 0 times u, the scalar 0 times a vector u, is equal to the zero vector for any vector in any vector space or any subset of a vector space, if H does not contain the zero vector, it can't be a subspace because it is not closed under scalar multiplication. So remember, closure under scalar multiplication means if I take any scalar, say alpha, multiply it by any vector in H, and that vector, alpha times u, has to be in H. This is scalar closure. And if we let alpha be 0, since alpha can be any scalar in the field, including 0, if we plug in a 0 for alpha here, we get 0 times u. And as we saw in the vector space lecture, the 0 scalar times any vector u is always equal to the 0 vector. That was a theorem that we proved. So this is a nice little check. If this is not true, if the 0 vector is not in H, then H is not a subspace. However, the converse is not true, and we have to be very careful about that. Just because the 0 vector is in H does not mean that H is a subspace. So we can summarize that like this. If 0 is not in H, then H is not a subspace. If 0 is in H, 0 is an element of H, then it might be a subspace. In practice, we check to see if the 0 vector is in H. If it's not in there, we're done, and we say H is not a subspace. If it is in there, then we're not done. It might be a subspace, it might not be. We basically don't have any information. So we have to check to see if H is closed, according to the definition. So here's an example. Let H be the set of vectors u and C3, such that u is equal to 3t, 0, minus 7t, where t is just a complex number. And we want to know, is H a subspace of C3? Well, clearly it's a subset of C3 because it's defined to be vectors in C3. So now we need to check closure. But first, we can check to see if the 0 vector in C3 is in this set H, because if it's not, then we're done. We know that H is not a subspace. Well, if we let t equal 0 here, t can be any complex number. So if I let t equal 0, I get 0 here and 0 here, and so I get the 0 vector. So when t is equal to 0, I get the 0 vector in C3, and so the 0 vector is in H. So that means we have to check closure. A really common mistake is to conclude that because the 0 vector is in H, H is therefore a subspace. That's a question that people often get wrong on quizzes and exams, so it's important to watch out for that. Okay, so let's check closure. How do we do that? We choose two arbitrary vectors in H. We form a linear combination of them. So I say u is this arbitrary vector in H, v is this arbitrary vector in H. We form a linear combination and see if that linear combination is in H. That's it in a nutshell. Let's break this down step by step. First of all, let's review what we mean when we say arbitrary vectors. We mean as opposed to specific vectors. So actually we'll start looking at some specific vectors. These are 3 of the infinitely many specific vectors in H. The vectors in H are in the form that was given in the definition, 3t, 0, minus 7t, where t is any complex number. So basically take any complex number you want, multiply it by 3, that's the first entry. Then the second entry is always 0, it doesn't depend on t. It doesn't depend on the number that you chose. And then multiply that same number, t, by minus 7, and that's the third entry. So in this first one, I just let t equal 1. 3 times 1, 0, minus 7 times 1. Then I said, let's choose 5. 3 times 5, 0, minus 7 times 5. Then I picked minus 2, 3 times minus 2, 0, minus 7 times minus 2, and we could go on forever picking any complex numbers that we want and multiply that number by 3 for the first entry. The second entry is always 0, as you can see all the way through here, and the third entry is always minus 7 times that number. But in order to check closure, we need arbitrary vectors. The only difference between an arbitrary vector and a specific vector is we don't choose a specific number for the variable here, which is called a parameter. But if we want to choose 2 distinct or different arbitrary vectors, then we need to use different letters. So this vector is 3t, 0, minus 7t. This one is 3s, 0, minus 7s, but it's not, this vector is not equal to this one necessarily. These two vectors would only be equal if s is equal to t. But in general, we don't assume that t and s are equal, and so these two vectors are not equal. What they have in common is that they're both in H. They're both in the form of a vector that's 3 times some number, and then 0, and then minus 7 times the same number that we multiplied up here in the first entry. So just change the letters, 3p0 minus 7p, 3q0 minus 7q. So we could write down infinitely many arbitrary vectors as well, just changing the letters. Okay, we come back to our example. We called this vector u, we called this one v, just to make it a little bit easier to write down this linear combination. We choose some arbitrary scalars alpha and beta, and we form this linear combination. This is really important. If you want to check closure, you always do the same thing. You form a linear combination of two arbitrary vectors in the set. And then you decide, is this linear combination also an arbitrary vector in the set? In other words, can this vector be written in the form of 3 times some number, 0, and minus 7 times the same number that's in the first entry? Well, to decide that, we just use the properties of scalar multiplication and vector addition in the vector space that H is a subset of, in this case, C3. So we write out alpha times U plus beta times V, and then we distribute the alpha and the beta in here and here, and then use the definition of addition and add the components together. And I skipped a step here. When I added these two together, I factored out a 3 from both terms here. Likewise, when I added these two together, I factored out a negative 7. And now I can see that this is in the form of 3 times alpha t plus beta s, and then this down here is in the form of minus 7 times alpha t plus beta s. If I just call alpha t plus beta s some new letter like gamma, then the vector here can be written as 3 gamma 0 minus 7 gamma, which is in the form of an arbitrary vector in H. In other words, it's 3 times a number, 0 minus 7 times the same number. So, since this linear combination can be written in the form of an arbitrary vector in H is closed under vector addition and scalar multiplication, and therefore it's a subspace of C3. Here's a handy theorem that makes this even easier in some cases. If S is a set of vectors v1, v2 up to vp, and it's a subset of vectors in a vector space V, then the span of S is automatically a subspace of V. This is really handy because if we, instead of checking closure, if we can figure out that a given set is the span of a subset, then we know it's a subspace. The proof of this theorem is very much like the example that we just did. We're going to define H to be the span of S, just so it's a little bit easier. We won't have to write the brackets around the S. And we want to see, or we want to show that H is a subspace of V. So we're going to let U and V be in H. Well, if U and V are in H, that means they're in the span of S. That means they can be written as a linear combination of these vectors. So here's U written as a linear combination of the V's, and here's V written as a linear combination. So I've used alphas for the coefficients on the V's for U, and then I've used different scalars, betas, same V's for V. So now, as before, we form this linear combination. So I've got two other scalars, gamma and delta, times U and times V, and add them together, and I see is this linear combination also in H. And we simply use the properties of vector spaces to show that. So I replace U with the linear combination I had before, and here's the linear combination for V, and then I distribute the gamma in using the distributive property, one of the distributive properties in the vector space axioms, and then I add all these terms up and factor out the common factor of V sub I, and I skipped a couple steps there. I would get to this, and then this is just a bunch of scalars. So this would be gamma alpha 1 plus delta beta 1, and then I increments to 2, and I'd get gamma alpha 2 plus delta beta 2, and it would keep going up to p. So I'd have a set of these scalars, psi's, the Greek letter psi looks kind of like a squiggly e, as I goes from 1 to p. So I'd have p of these, one for each of the v's, and they're just gamma alpha sub I plus delta beta sub I. And here is gamma u plus delta v down here equal to, well, this is just a linear combination of the vectors in H, and so this vector is in the span of H. So since our linear combination can be written as a linear combination of the vectors in H, therefore H is closed under vector addition and scalar multiplication, and it's a subspace. So that was a little bit of work to do that proof, but the good news is we can use this result now and avoid doing this kind of work in the future. So let's try that same example we just did again. Here's H, same set that we had before. Is H a subspace of C3? Well, if we can write H as the span of some other set that is a subset of C3, then theorem 1.1 that we just saw tells us that H is automatically a subspace and we don't have to check closure. So if I write down H here, if I notice that there's a factor of t here, and I just factor it out of the vector using the definition of scalar multiplication in C3, this set is the set of all vectors u that are a scalar multiple of 3, 0, minus 7. T is just any scalar. So H is the set of scalar multiples of 3, 0, minus 7. So we can write H like this. It's the span, the angle brackets means the span of the set containing this one vector 3, 0, minus 7. And this set is a subset of C3. Therefore, by theorem 1.1, H is a subspace of C3. Now that we know what subspaces are, we can look at a few results about subspaces. We'll see a few theorems that talk about other sets that we've talked about and show that they are subspaces. First one, the null space is a subspace. So the null space of a matrix, we learned what that is earlier, and the word space in the definition was intentional. It refers to a subspace. So the null space is a subspace. Remember the definition of the null space. If A is an n by n matrix, the null space of A, written n of A, n with A in parentheses, is the set of vectors x in Cn such that Ax equals 0. Okay, so the theorem says if A is an n by n matrix, the null space of A is a subspace of Cn. So we know that the null space, by definition, is a bunch of vectors in Cn. It's a set of vectors in Cn. This theorem is taking it a step further and saying, well, this set of vectors in Cn is actually a subspace of Cn. And the proof is very straightforward. It just checks closure. So if we let u and v be in the null space of A, well, if u and v are in the null space of A, that means A times u equals 0 and A times v equals 0. Because by definition, if x is in the null space, Ax equals 0. So if u is in the null space, Au equals 0. If v is in the null space, Av equals 0. And we form a linear combination, as always, to check closure. So we take these two arbitrary vectors in the null space, u and v, and they're arbitrary because I haven't written down some specific set of components for these. I just gave them letters as names. I formed the linear combination with the scalars alpha and beta, alpha u plus beta v, and then I'm going to check to see if this linear combination is in the form of a vector that's in the null space. Well, it's got to be one of these x's. And what's so special about the x's? Well, when you multiply the x by a, you have to get 0. Well, let's see what happens when we multiply this linear combination by a. We use the properties of matrix multiplication and scalar multiplication and vector addition in Cn. So we distribute the a into the alpha u and the beta v, and then we can factor out the alpha, just switch the order of the multiplication and factor the alpha outside here and factor the beta outside the a. And then we can use the fact that both u and v are in the null space. So au is 0, so this term goes to 0, and av is 0, so this term goes to 0. So I simply have some scalar alpha times the 0 vector, well, that's 0. Some specific scalar beta times the 0 vector, that's also 0. The whole thing adds up to 0. Okay, so what does that tell us? Well, it tells us that a times this linear combination is 0. Well, that means it's in the null space. So this linear combination is in the null space, and the null space is therefore closed under vector addition and scalar multiplication and is a subspace. Another theorem says that the column space of a matrix is also a subspace, and in particular it's a subspace of Cm. So if A is an m by n matrix, well, the columns of A will have m components, so there'll be column vectors in Cm. We already know that the column space is the span of the set of the columns of A, and so now we're claiming that that is a subspace. Well, we can use theorem 1.1 very easily in one sentence in the proof here. Since the column space of A is defined to be the span of a subset of vectors in Cm, namely the column vectors of A, it's a subspace of Cm. And from that theorem, we can get this one pretty easily, if A is an n by n matrix, the row space of A is a subset of Cn. Well, A transpose is n by m, and the row space of A is defined to be the column space of A transpose. Using the theorem we just proved, theorem 1.3, the column space of A transpose is a subspace of Cn. Why is it a subspace of Cn? Well, because A transpose is n by m. A transpose is n by m, so notice m was the first letter here, and the column space of A is a subspace of Cm. So n is the first letter here, so the column space of A transpose is a subspace of Cn. All right, so the column space and the row space of a matrix are both subspaces. And that finishes this video on subspaces. So now you should be able to define what a subspace is, and more importantly, decide if a given subset of a vector space is actually a subspace.